Hi, everyone. This is Julia Haggerty. I'm the Interim Director here at the Institute on Ecosystems, and I want to welcome you to this week's Rough Cut seminar. It's wonderful to have you all here, and I know a few more people will filter in as we get started. Just a reminder that this webinar is being recorded, and we'll follow our standard format of a presentation with time for questions and answers at the end. Before we start, let me also tell you that the next Rough Cut will be 2 weeks from today, and will feature Bryce Maxwell and Jessica Mitchell from the Montana Natural Heritage Program. So we look forward to seeing you at that. So without further ado, let me introduce one of our favorite scholars here from Montana State University. That's Christopher Schiller. Christopher Schiller is a paleoecologist who received his bachelor's in science and geology from South Dakota School of Mines, and then came to MSU, where he has just finished last fall, a PhD in earth sciences, and now he is a postdoctoral fellow. So we're looking forward to hearing about Chris's work, and thank you all for joining us today. And I'll turn it over to you, Chris.
Thank you, Julia. So today I thought I would discuss a little bit of the work that the IOE here helped fund through the Yellowstone Research Fellowship I was given as a PhD student. And really that work was focused on exploring the role that hydrothermal activity has had in shaping the Yellowstone ecosystem. So we'll go through some of the work that's been done that's been done as part of that project. And the spirit of Rough Cut Science, I'll leave a few more open-ended hypotheses at the end, and some of our future research that we're considering exploring for any input or questions this audience may have. So I'm gonna challenge you to think about an ecosystem we're all quite familiar with, the Yellowstone ecosystem, both the greater Yellowstone ecosystem and Yellowstone National Park itself, perhaps in a slightly different way than one might be accustomed to. And we're gonna use the terminology that Ken Pierce and Lisa Morgan at the USGS have really pioneered, describing the Yellowstone ecosystem as a geoecosystem. And primarily what's meant by this is that the Yellowstone ecosystem is really dictated by geologic processes that are associated with the Yellowstone hotspot tract. So this quote comes from Pierce et al. 2007, that geologic processes associated with the tract of the Yellowstone hotspot have a profound effect on the geography, topography, climate, soils, and biota of the greater Yellowstone ecosystem. So there are many examples of this. One of the classics is looking here at the hotspot tract itself and the Snake River Plain that leads up to the Yellowstone Plateau as a corridor by which moisture from the Pacific, primarily winter storms, really dictate the climate condition that we see in Yellowstone. So a lot of winter storm tracks come up the Snake River Plain and will really dump out a large volume of snow over the Yellowstone Plateau, as you can see here. So the surrounding hotspot geology has a lot to do with the climate that we see expressed at Yellowstone. And the Yellowstone, my mistake, I'm trying to get rid of my annotations now. Trying to get fancy here. All right, so the Yellowstone geology has dramatic effects on soil and ecology as well. So many of the rhyolites that have been produced by Yellowstone volcanism, either airfall or ignimbrite tuff deposits, like you would see if you drive through Golden Gate in northern Yellowstone National Park, or if you're driving through the central part of the park and see these extensive rhyolite lava flows that you can see here on the left. All of those rhyolite deposits produce very sandy, nutrient-poor soils that give way to all of these lodgepole pine forests that we see throughout the park. These truly monotonous stands of lodgepole pine, which really dominate the Central Plateau, create much of the fire regime that's present in Yellowstone, very high severity, intermediate frequency type fires, such as was exemplified in the fires in 1988. So there are a lot of processes by which we can see the clear impacts of geology, both on a regional scale and at a more local scale, in impacting the ecology of Yellowstone. So we might call it a geoecosystem. It'd be very fair, however, at this point to just say that, well, by this logic, really every ecosystem on planet Earth is a geoecosystem. Every ecosystem is in some is to some degree the product of the topography created by regional geology and by the soils produced by the underlying substrate. But what's unique about Yellowstone is that some of these geologic processes are happening on short enough timescales that we can study their impacts in a more dynamic way. And of course, I'm referring to here is the hydrothermal activity that we find in Yellowstone. So this is a map of the park produced by Hurwitz and Lowenstern, and you can see in black and in green throughout the park, mostly concentrated within the Yellowstone caldera, all of these vast thermal areas that really the park is well known for. And we know that these thermal features do have an impact on park ecology. This is pretty clearly seen when we look at what are informally referred to as bobby sox trees, and these are lodgepole pines that have been killed by hot mineral saturated fluids, alkali fluids as well, that are spilling across the landscape, which kill the trees and leave these little bases of silica impregnated wood that look like bobby sox. So it's clear that they've got an impact here, and we can see it on a larger scale as well. Greg Vaughn last year published a study documenting the development of a new thermal area in Tern Lake, which is in central eastern Yellowstone National Park. If you focus on this lower area circled in red, beginning in 1994, you can see that the area becomes less densely vegetated. It's cleared of all these lodgepole pines, and eventually you can see the development of hydrothermal rock deposits taking shape here. So you can see that both on local scales with these kinds of trees being damaged by hydrothermal activity, and on larger scales with the development of these thermal areas, hydrothermal activity has a pretty clear impact today on the shape of Yellowstone ecology, at least where hydrothermal activity is present. So today what I'd like to really focus on is how we've tried to explore what these impacts might have been in the past. So we will look at hydrothermal and some volcanic events as ecological disturbances, and I'll explain what that means here in a slide or two. We'll talk about landscape development where hydrothermal activity is probably more pervasive than any other place in the park, Lower Geyser Basin. And finally, we'll spend some time in a more hypothetical realm, laying out some competing hypotheses for what might be causing some of these changes in the Yellowstone geoecosystem. So as we go through, I'd like to just call a quick shout out of some of these works that have been compiled into papers or papers that are currently in progress. So this is one that I've done with some folks here at MSU, Kathy Whitlock and Pico Alt, and also with Lisa Morgan at the USGS. And we decided to go looking first for impacts of hydrothermal activity where it looked most obvious to us in the landscape. So a really dramatic example of hydrothermal activity influencing the landscape are through hydrothermal explosions. So these are a couple examples of what hydrothermal explosions have looked like in the historical record, both at Excelsior Geyser in the 1880s. There was a series of explosions which ejected rock and created a widening crater at Excelsior Geyser in Midway Geyser Basin. And this explosion in Biscuit Geyser Basin that was by sheer happenstance photographed by a volcanology field trip. Explosions in the past were quite a bit larger though, and we suspect that it may have had an impact on local ecology. So for comparison, here is a place called Turbid Lake in eastern Yellowstone. This is just northeast of Yellowstone Lake. And this area here with this rim of high terrain that you can see around the lake is an apron of hydrothermal explosion breccia that is considerably larger than what we saw before. And this feature is nearly 1 kilometer in diameter. So some of these events were clearly much larger in the past. and they leave behind some pretty impressive deposits. So this on the left is a photograph of a wave-cut terrace in an outcrop along the north shore of Yellowstone Lake. And these deposits that we can see in the lower and upper part of the picture, these conglomerate breccias, these are deposits created by hydrothermal explosions that have covered very large areas in the past. So you can see on the map in the lower corner here, with the scale bar being 7 kilometers, they've covered quite extensive areas of Yellowstone. And this is a very conservative map. In fact, we found some of these explosion breccias very far-flung locations from their craters. And this Mary Bay explosion, whose crater is located in the northern part of Yellowstone Lake, is perhaps the largest hydrothermal explosion that we know of in the history of planet Earth. We see these explosion deposits in some of our lake sediment cores, and that's what's going to allow us to try to parse apart what the ecological impact might have been. So what we did is we collected some of these sediment cores, both from Yellowstone Lake, here this red dot, and from Cub Creek Pond, a small lake east of Yellowstone Lake. And we tried to parse apart the vegetation history before and after these explosions using pollen analysis. You can see here the sampling strategy with some samples before the explosion and samples after the explosion. So what did we find? Well, we'll look at a couple of these plots. So I'll explain this ratio here. This is the ratio of arboreal pollen to non-arboreal pollen. Quite simply, values that are plotting higher on these graphs mean that there is more tree pollen, and values that are plotting lower on these plots indicate that there is more herb and sagebrush pollen. So here, negative values are before the explosion, and these red lines represent these deposits found in these various cores. And we find after a few of these explosions, there seems to be a noticeable impact on the landscape. So first, looking up at the top plot at Cub Creek Pond, there's quite a bit of variability in the relative amount of arboreal and non-arboreal pollen, but the value declines to its lowest value of the record immediately after the explosion. And we think this correlates, this represents rather the conifers in the vicinity of the pond were being damaged or killed by the explosion itself. We can see this more clearly at Yellowstone Lake, this second plot from the top. This curve looks to be relatively stable before the explosion, and again declines to its lowest value of the record quite abruptly after the explosion. So in these top two explosions, which happen to be the largest explosions that we know about, we think that we're seeing some sort of definite impact from the explosion deposit. These lower deposits are smaller events, and we don't think had a lasting impact. Another way we might look at these data to try to really parse out what that ratio of arboreal to non-arboreal pollen means is we can actually plot out the influx, the actual number of grains per square centimeter per year of these two pollen types that were being deposited. So actually how much conifer pollen was being deposited in the lake versus how much non-arboreal pollen, sagebrush, grasses, that kind of thing. And what we see is that across this threshold, it's really a matter of conifer pollen, this arboreal pollen, this green line, is declining across this threshold, while the non-arboreal pollen curve is either declining less significantly or even slightly increasing. So this confirms again to us that this is definitely a record of some sort of mortality or stress event in conifers near these lakes related to this explosion. As opposed to some sort of other impact that could have impacted the herbs and the sagebrush. So we think we've got some evidence of there being at least a very short-lived impact from these explosions. And it's really only evident immediately above these deposits. And as soon as you get well above these sediments, they quickly return to pre-explosion conditions. So for the sake of comparison, like how significant is this? Let's compare it to a somewhat comparable event, at least in the Yellowstone landscape. And this event is the Mazama ashfall. So the Mount Mazama was the volcano that existed prior to the creation of Crater Lake. It was a very large stratovolcano in the South Oregon Cascades. and it produced the most explosive volcanic eruption in North America in the last 12,000 years. That event deposited quite a bit of ash throughout the greater Yellowstone ecosystem. And here you can see in Yellowstone, at sites where we've been able to study, it's between the 5 and 1 centimeter isopachs of this relatively recent map. So we think that there's at least a little bit of ash that was deposited throughout this region. And indeed, that is the case. Here's another image of a sediment core from Yellowstone Lake. And this is the thinnest deposit that we found. It's perhaps just a few millimeters thick. So to compare the impacts of the hydrothermal explosions to this ashfall, we've engaged in a very similar procedure, and we've looked for the impact, the vegetation history before and after the ashfall. So looking at a very similar plot where values that plot higher on these curves represent more trees and shrubs, and values that are lower represent more herbs and more sagebrush. And what we can see at all of these sites, of which the lower 2 are in Yellowstone, there is a much more dramatic effect, where this value that is quite clearly more stable before and after experiences very, very low AP-NAP ratios. So it's tempting to think that there was a very similar effect, perhaps of greater magnitude, following this little ashfall event in Yellowstone, compared with these very locally dramatic hydrothermal explosions. But that's not the case. When we tried to make this comparison, we found out that the influx was driven by a very different trend. So again, in these plots, the green line represents the total amount of mostly conifer pollen raining into the lake, whereas the orange line represents the total amount of herbaceous and sagebrush pollen that's raining into the lake. And we can see that the trend is very different. Here we have a dramatic increase in herbaceous pollen, and sagebrush pollen that's really driving the curve. So it's not the same kind of event that these hydrothermal explosions and Mazama look very different. They're both very short-lived, but there's something different going on following these Mazama ashfalls. And what we think it is that the deposition of fine-grained ash may have increased the ability of these arid steppe soils, where all these herbs and sagebrush are growing, to retain moisture, make them more tolerant of drought. So we think instead of the conifer mortality that we saw after the hydrothermal explosions, after Mazama, we instead have a proliferation of mostly sagebrush. So they don't turn out to make a great comparison to one another. But an important takeaway from both is that there's relatively quick recovery, that whether these ecosystems were impacted by hydrothermal explosions or these ashfalls, it seems that the impact to the ecosystem was quite short-lived. So that's a little bit of a strange finding in our mind, especially given how dramatically we suspect that these deposits must have altered the soil, the soil conditions where they were deposited. But we thought to ourselves, maybe we'll go and we'll look in an area where we might have more pervasive and maybe more long-lived impacts of hydrothermal activity. So the place we're going to look is in Lower Geyser Basin. And this is part of a study that we are rapidly approaching a submission on, where myself and Kathy Whitlock, along with Sabrina Brown, a diatomist at Defiance College, have been working on. So if we want to look for the impacts of hydrothermal activity, I don't think there's a better place to look than Lower Geyser Basin. It's located here along the Grand Loop Road in western Yellowstone. It's a very famous, very tourist dense area. It's where fountain paint pots are located. It's very close to the Midway Geyser Basin, Clepsydra, and a whole variety of famous geysers themselves exist in Lower Geyser Basin. We originally went looking in Lower Geyser Basin because we thought we could find the impacts of more hydrothermal explosions. As you can see on this map, indicated by these little basin, this basin symbology, there are 3 very large hydrothermal explosion craters found in the vicinity of Lower Geyser Basin. Our sediment cores did not turn up any evidence of hydrothermal explosions, but we were able to find from a core taken from Goose Lake, some other evidence of past hydrothermal activity and the response of the ecosystem to it. So to just paint a further image of Lower Geyser Basin, as opposed to the forests that were impacted by those hydrothermal explosions around Cub Creek Pond and Yellowstone Lake, areas which are, for the most part, pretty densely forested, Lower Geyser Basin is comparatively open. And you can see really three distinct types of landscapes in this image. Beyond the geyser basin, where soils are very cool, you have the very typical, very monotonous lodgepole pine forest. In the background here, you can see that there's quite an extensive grassland. And in the foreground, there is this active thermal, the thermal flat, which is mostly composed of siliceous sinter being actively deposited by hydrothermal features. What's interesting about Lower Geyser Basin is it's also been the focal point of a lot of past studies of the impact of modern hydrothermal activity on vegetation in Yellowstone, which has the interesting finding that not unlike algae, like within and microorganisms within thermal features themselves, which organize themselves in different communities based on the temperature of waters within a thermal spring, there's actually zones of vegetation out on the landscape as well. And what they found is that temperature and to a lesser extent acidity are going to strongly dictate the types of vegetation that we see in the geyser basins themselves. So the landscape is very much a product of hydrothermal activity with these diminutive grasses out here, a lot of alkali grass, a lot of panic grass, and not a lot of sagebrush, is itself a thermal community, well adapted to tolerating these warm, slightly acidic soil conditions. The other thing that's wonderful about Lower Geyser Basin is it has these lakes that allow us to study the past ecology of these systems. So we collected a core from Goose Lake. This is an image from the day we collected our core. And you can see it's set slightly apart from the rest of Lower Geyser Basin. There is a little bit of lodgepole pine in the vicinity, and a lot of the area is presently non-forested, which is probably a legacy of the '88 fire. But for the most part, it is in close proximity to, and we think, a good place to study the history of Lower Geyser Basin. So we collected some wonderful sediment cores in 2018. And here's most of that core. And immediately there's something that's very striking. Right about here, there is a very sharp contact in the sediment where we go from very brightly laminated sediments below to more dark, organic, rich-looking sediments above. So there's clearly some sort of history going on at this site, some sort of dynamic history. So we've done some lithological and geochemical analyses, and what we think we've discovered is there's something of a history of hydrothermal activity from the sediment core. So I'll gray out some less important features of this plot, and I invite everyone to look at a transition that occurs here at 178 centimeters in the core depth. Now that's that same contact that we saw in the previous image, and it's marked by very stark changes in geochemistry. So the sediments in the core themselves are both enriched in arsenic, and when we've done stable carbon isotope analyses, we found that those sediments are also characterized by very heavy carbon isotope values. So for reference, these carbon isotope values, if they were in the vicinity of between -30 to -25, that's a very terrestrial vegetation signature. Values more between -20, -15 is much more of an aquatic vegetation signature, but we're getting some very strange values in the vicinity of like -10. So we think that this represents the signature of volcanic carbon entering the sediment, probably through like hydrothermal activity. And similarly, we think all of this arsenic enrichment in the sediment probably comes from hydrothermal activity. In addition, we found another little exciting piece of geology within this core, and that's this layer here, which I think is roughly orange sherbet in color. It was very unusual when we looked at the geochemistry. It was dramatically enriched in antimony relative to the rest of the core, which struck us as very bizarre. And with the help of folks at the iCal lab here at Montana State, we were able to do some SEM and X-ray diffraction analyses, and we found that it's this very fine-grained spherolytic sediment that contains almost 85% fluorite. So it's this little deposit of fluorite. Taking these three pieces of evidence together, the fact that there's apparently volcanic carbon in the system, it was very arsenic rich, and that we have this instance where it deposited nearly relatively pure fluorite, we think that we have some evidence of hydrothermal activity at Goose Lake, which is kind of interesting. We think that we actually have record from this site of the history of a thermal feature that either existed within Goose Lake or very near to it. And what's more, if we flip back to the previous slide, we have evidence of when it was active and when it shut off. So this is going to form the basis of our argument about the ecology. So we'll compare these inferences from the geology, from which we're able to parse out something of a crude hydrothermal history, at least for this site, and compare it to basin-wide vegetation. So let's have a look at that vegetation. This is the only complete pollen diagram I'm going to show in this talk, which I'm not of a cruel state of mind, but I want to draw everyone's attention to two particular facets of this curve. And these are the two dominant pollen types that we found in this sediment core. A lot of the pollen is unsurprisingly pine. We think from previous studies that lodgepole pine probably established on this landscape about 11,500 years ago. So the fact that in this 10,000 year long core, we found lots and lots of lodgepole pine is not surprising. And the other major component is artemisia, is sagebrush. Now, I said that there's not a lot of sagebrush growing in Lower Geyser Basin today. There are some incidental patches of certain varieties of artemisia, tripartita mostly. But a lot of this could be very distally transported. A lot of this could be coming from as far away as the Snake River Plain. So what do these curves show between these two dominant pollen types? First, there's this long-term trend of steadily increasing abundance of pine pollen. And to us, this suggests that the forest is gradually becoming more and more closed or is encroaching into the basin. And this is pretty typical for most records we see in the region, and we'll show that in just a moment. After about 3,800 years, though, there's a switch, and the pine is diminished to the present. So the amount of pine increases to about 4,000 years and then decreases. And most of that slack is taken up by artemisia. Similarly, we looked at the charcoal that was found in this core as a record of fire in Lower Geyser Basin. And we found that similarly, when the forest became its most closed, there was the most fuel available, fire activity really took off, and we have a lot more burning that takes place in the middle Holocene. And then as we head to the late Holocene, as vegetation seemed to open up, there's less fire, which is a pretty consistent finding. Our collaborator, Sabrina Brown, also produced a wonderful diatom record from Goose Lake for us. And there are two factors, two taxa that I like to draw your attention to. And these are Navicula wildi and Diatoma maniliformis. The important thing about these diatoms is we know their autoecology pretty well. We know what conditions they thrive in. Navicula, on the left, the species really has wide pH tolerances, that it can tolerate fairly acidic to even slightly alkaline water chemistry, compared with Diatoma maniliformis, which is something of a high temperature specialist, that it's found growing at relatively warm temperatures. It likes temperatures to be above about 15 C on average, and it can tolerate much higher temperatures. It's been found in bizarre locations, including like the coolant discharge channels of nuclear power plants. What's interesting, at that same point where the vegetation is opening up, it seems that the abundance of these diatoms, which have broad pH tolerances and prefer warm conditions, seem to drop off, that there is this lower period where they're quite abundant and then they drop off quite wildly. So this poses the question of, can we draw some combined history here? So let's see if we can't compare these data sets and really see if we can't bring this back to comparing the hydrothermal activity to what's going on with the ecology, both the limnobiota, the life inside the lake, and terrestrial vegetation. All right, so let's start with thinking about the region without hydrothermal activity. So this is the summer insolation anomaly over the last 10,000 years. This represents the actual amount of solar radiation that impacts a certain square footage of the Earth's surface. And we can see that there is a very smooth curve going from very high summer insolation in the early Holocene, maybe a couple degrees warmer in the summers is what this would mean, to conditions today, which are greatly diminished summer solar insolation. So this means warmer summers, probably effectively drier summers, to cooler summers. And regional vegetation has responded to this solar forcing. So these are AP-NAP curves, much like we were looking at earlier in the talk, where values to the right mean more trees, values to the left mean fewer trees. And at each of these sites, within and very close to the lodgepole pine region of Yellowstone National Park, we can see that for the most part, the amount of arboreal pollen has increased over the last 10,000 years. So all of these curves seem to be gradually increasing over the last 10,000 years. Yellowstone Lake is a little bit of an exception for some kind of technical pollen analysis reasons, but all the same, it increases until about 6,000 years, and then it remains relatively steady. As we would expect with the forest becoming more dense at these sites, fire activity, where the record is available, seems to be responding overall to this increased available biomass. So over the last 10,000 years, the amount of total charcoal accumulation at Signet Lake, where there's also a charcoal record, seems to be increasing. The overall amount of fire activity at Signet Lake seems to have increased as the forest has gotten more dense, as the climate has gotten cooler and wetter in the summers to accommodate it. That's sort of the regional story. But let's contrast that with what's happening at Goose Lake. So at Goose Lake, we're converting those pollen data to an AP-NAP curve. And we can see that for the early and middle Holocene periods, the record is quite similar to these other lakes, where the total amount of forest cover is increasing. That AP value is increasing. We're getting more and more trees in the landscape, either as the forest around Goose Lake is becoming more dense, or as it's becoming more extensive, again, encroaching further into the basin. But that's where the similarity ends. As we can see here, at about 3,800 years or so, vegetation reverses itself and becomes considerably more open. And this is not a trend we see at other sites on the Yellowstone Plateau, and it is not a trend easily explained by the climate trend at this latitude. Similarly, the fire record does not look similar to Signet Lake at all, despite very similar lodgepole pine vegetation near both, where fire activity increased pretty dramatically at Goose Lake in the middle Holocene, but again decreased in the late Holocene. And what's interesting is that these trends in the terrestrial ecosystem mirror that trend we saw in the diatom data. If we look here again at the Diatoma maniliformis curve, but it's also the same time where we have that change in hydrothermal activity. So again, to remind everyone, this is the black curve, is that arsenic curve, which we think is our best proxy of hydrothermal activity at Goose Lake itself. So at Goose Lake, there seems to be a record of hydrothermal activity chugging along, happy and glorious until about 3,800 years ago, where that hydrothermal activity abruptly shut off at Goose Lake. Synchronously, it appears that the vegetation at within Lower Geyser Basin seemed to have opened up and burned less. So there's this site, this story that's a very local site-based story, where at Goose Lake, hydrothermal activity was present and then abruptly shut off. And at the same time, there's this basin-wide story where the vegetation, as evidenced by its pollen, seems to have been getting more and more dense, kind of doing what we would expect climate to be enforcing, and then suddenly reverses itself and becomes more open. So we think what this represents is that about 3,800 years ago, there was some dramatic reorganization of hydrothermal activity at Lower Geyser Basin that created the modern, mostly treeless landscape we see today. So this would, in our mind, explain how we could have a shutoff of hydrothermal activity at one site, but apparent opening of the landscape basin-wide. So again, this vegetation in Lower Geyser Basin is itself a thermal vegetation regime where these grasses, this grassland that exists, and these non-vegetated areas are enforced by heated soils and thermal discharge. And we think that the fact that these two are happening simultaneously, that there is some underlying hydrothermal mechanism that caused a synchronous change at both. And we think this is probably a better explanation than climate or some other disturbance-based mechanism, because those factors are happening so synchronously. All right, so to summarize that pile of seemingly unrelated data at Goose Lake, we think that hydrothermal activity in Lower Geyser Basin underwent some major reorganization at 3,800 years ago that caused a synchronous shutoff of hydrothermal activity at Goose Lake itself, but then more widespread hydrothermal activity elsewhere in the basin. And clearly this impacted long-term Holocene scale vegetation development, which is why the vegetation record at Goose Lake looks nothing like what we found at these other sites, at Cygnet Lake, Loon Lake, or Yellowstone Lake. This leads us to our last point. As we consider that we think that there was some abrupt change in hydrothermal activity in Lower Geyser Basin at about 3,800 years or so, that seemed to have a major impact on the development of vegetation in that area, it leads us to the question of, so what happened? What might have caused these past hydrothermal changes? And this is where we're going to get a little bit into the realm of future hypotheses. And my goal here is to lay out some competing hypotheses, try to be a good earth scientist and lay out these different possibilities, and see if we can't create a few different plausible hypotheses for what could cause hydrothermal changes in Lower Geyser Basin that created such profound changes in the geoecosystem of that basin. So some things that immediately come to mind: there could have been some geophysical trigger that altered the geoecosystem. Earthquakes or ground deformation related to the Yellowstone caldera are the immediate ones that come to mind. It's possible there could be hydroclimatic changes, such as multi-decadal drought, and we'll have a look at why that might be a feasible hypothesis in just a moment. Or some internal hydrothermal cause, which is going to be a little bit of our, is going to be the least testable of these hypotheses. But let's have a quick look at why these might be feasible. So much as I showed earlier, we know that some geophysical processes like earthquakes can dramatically impact hydrothermal activities. That case study we looked at early in the talk of that new thermal area developing at Turn Lake was probably caused by some combination of ground deformation related to the Yellowstone caldera and other factors. A more famous example, it relates to the development and change of hydrothermal systems following the 1959 Hebgen Lake earthquake near Yellowstone. Very large earthquake that had an impact on a huge variety of hydrothermal features in Yellowstone Park. The most famous of these is Seismic Geyser in Upper Geyser Basin. So just for reference, it's pretty dramatic to see this. These are images taken by George Marler at the place that would become Seismic Geyser over a period of many years. This is spring of 1960, where a fumarole developed, where a fumarole did not previously exist before the earthquake. Here is that same feature, which is developed into a geyser in spring 3 years later. And if we look at a picture taken from about the same location in June of 1974, we can see that the whole landscape has changed, that much more of the landscape is devegetated, and that a proper spring that exhibits geyser activity is developed. So it's quite feasible in our minds that some geophysical process, such as earthquakes or ground deformation, just that could be a feasible cause for the change we observe at 3,800 years ago in Lower Geyser Basin. Another interesting addition to this idea is that we do have seismic activity that was occurring at this time. There's evidence from a study that Bill Locke, Grant Meyer, and another co-author I'm callously forgetting did. This is here around Yellowstone Lake at a place called Eagle Bay. There's a pretty famous fault system there called the Eagle Bay Fault. And based on a combination of the morphology of the fault scarp and some relative dating based on radiocarbon and obsidian hydration dating, we think that there was some earthquake activity that occurred in this vicinity at about 3,300 years ago, which is roughly the time period we're thinking about and might be caught by the uncertainty of our ages. So this is at least provides a potential mechanism and gives credence to this as a potential hypothesis. There's some ongoing work to characterize some turbidites and some other potential seismic related deposits in Yellowstone Lake. So we might have a better record of this going forward that might help us test this hypothesis better. But this helps us say, okay, not only is there a geophysical mechanism that might explain changes in the geoecosystem of Lower Geyser Basin, but there is an event that might partially explain it. Ground deformation is another option, and these are images from some pretty famous work done by Ken Pierce, Grant Meyer, and others working on the terraces around Yellowstone Lake. And for those who don't know, as you're looking at these pretty these meadow areas around Yellowstone Lake, there are all of these ancient shorelines here that form terraces along the shore of Yellowstone Lake. And the idea is that each of these terraces responds to a different period of uplift, of inflation or deflation of the Yellowstone caldera itself. And based on a pretty large set of radiocarbon dates, Ken Pierce has developed a chronology of what these look like. And what's important, if we focus on this part of the plot here, there is some evidence that about 3,000 to 4,000 years ago, there was a low stand in the caldera was really at its lowest, at a deflationary stage, and it began to rebound at about this time, which there's a variety of geologic evidence for. But again, the point here is that there's also ground uplift activity happening at this time. So that's a little far into the geology realm, and those are going to be difficult hypotheses for us to test. It's going to it be very hard to provide age models that could really pinpoint causes of individual events together. And a competing hypothesis that's also very interesting was suggested to us by Scholl Hurwitz at the USGS, who thinks that there is a strong hydroclimatic driver in thermal features that might also explain what's going on in the Lower Geyser Basin geoecosystem. So Hurwitz and others have been working on a study where they have been dating wood that is entombed around Old Faithful Geyser. So this is DEM right around Old Faithful, a little LiDAR imagery, I believe. For reference, these dashed lines are the boardwalks around Old Faithful. And around the cone, there are all of these trees that are, I believe, mostly in situ, that apparently at some point grew on the geyser cone that are all now long extinct. that were at the time extinct. So what they've done is they've gone and dated, with radiocarbon dating, a lot of these trees that seem to have been growing along the cone of Old Faithful, and they found something quite interesting. These are these dates in green, where most of these dates seem to date to the medieval climate anomaly. So a period in the 13th century where there was prolonged multi-decadal drought worldwide. So the hypothesis is that in this period of drought, both locally and globally, that the thermal features might have been affected and the Old Faithful geyser itself may have shut off during this period. So this leads us to believe that hydroclimatic forcings might also have an impact on the way geysers behave, and therefore might have an impact on how the geoecosystem took shape. We also think this might be a feasible hypothesis for our 3800 event, just because there's activity happening at that time as well, hydroclimatically, that we have evidence for in the region. So this is a new study by Chelman et al., where they looked at ice patches, so pieces of persistent ice in the Beartooth Mountains to the northeast of Yellowstone. And they found, right in this period, from about 4,200 to about 3,800 years ago, there is a period of what they infer from isotope data to be very warm winters. Which correlates to a global period of aridity that occurred at about 4.2, so about 4,200 years ago. So there's also some regional and global evidence that this event that we think happened at about 3,800 years in Lower Geyser Basin might have been driven by some sort of regional to global hydroclimatic event. So again, that's that black curve here, these isotope data here suggesting that at least in this region, there was certainly warmer summers than a lot of the rest of the record. All right, so with all this in mind, here's what at least we're thinking. This is what to us would be a reasonable approach to try to parse apart these competing hypotheses for what's driving changes of the Lower Geyser Basin geoecosystem. So the first thing that's quite clear to us is that in terms of establishing the driver, the hydrothermal activity in Lower Geyser Basin, we're currently really limited by the fact that we've only looked at one site. Those data, those geochemical data, really come from the sediments themselves and only produce a record of the hydrothermal activity at Lower Geyser Basin. So the idea is to go around now to a larger number of sites and see if we can't get a more complete spatial picture of what's going on with hydrothermal activity in this setting. So we're very lucky in Lower Geyser Basin. There happens to be quite a lot of bodies of water and wetlands that we might be able to try to core. So this might help us really parse out like how basin-wide was this change? Was vegetation at large responding to something that was happening, on a larger scale? We should see hydrothermal activity kicking in some of these other sites if that's the driver. So we really want to expand the number of sites that we're studying in Lower Geyser Basin. And the other thing that's quite clear to us is we need some record of climate change, particularly of hydroclimate, that's near the geyser basins, so we can test the hydroclimatic hypothesis that we can also date very well. So we're looking into some more sites in the vicinity that we might be able to produce a good record from, because in particular, we're very limited by our ability to date these cores. This is the last little tangent for this part of the talk here. Because these systems are hydrothermally impacted, we have a very persistent problem of getting bad radiocarbon dates from these sediment cores. So we think, which is evidenced by all of these little curves here above the line and these yellow curves here, these are all dates that are erroneously old, probably because of hydrothermal CO2. So we really need to make sure we're just outside of these thermal areas. Otherwise, we're going to get this conflated imagery of what's going on in the basin, and we're going to keep having bad age models. So those are kind of our two approaches on how we want to think about this going forward. And I'd be very curious if other folks have thoughts, if this is feasible, or if anyone else has thoughts about what could go to explain these abrupt changes in the geoecosystem of the geyser basins. So just to summarize the talk, We've looked at two different types of hydrothermal impacts in the Yellowstone ecosystem, both things that look like hydrothermal disturbances, so hydrothermal explosions impacting these systems. Very short-lived damage to conifers for the most part. They did not have persistent impacts on the ecosystem. And we really use Lower Geyser Basin as a case study for these hydrothermal settings where that history of that legacy of thermal activity is very important. And this needs to be expanded, both thinking of causal hypotheses, whether they be geophysical, hydroclimatic, or some internal mechanism we can't study, and really to explore the extent of these changes. Coming to a close, I just want to briefly thank, in addition to IOE for in my last year of my PhD helping to fund this work, all the people who helped me in the complete the research with my PhD, helped me not only collect data, but help guide my thinking on these topics. And of course, I want to make sure to thank all my co-authors on these manuscripts and all the folks that have consulted and and willingly helped us out on these questions in Yellowstone. And with that, I'd be happy to take any questions in the chat or otherwise, however you prefer to run it, Julia.
Wonderful. Thank you so much, Chris. Why don't you all turn your microphones on and give Chris a quick round of applause. Those are really wonderful. And yeah, I think we're a manageable group. So I see already some questions in the chat. And Chris, if you can see those, I can either read them or you can just take them. Up to you.
Chris, I think your mic is muted.
Let's see. There we go. Excellent. Thinking about how your temporal traces of the various pollen densities, how might climate change impact prevailing wind directions, and how could these wind directions significantly influence the densities of various pollens in these deposits? Thinking about spatial relations between pollen source and deposition point, and how far a particular pollen type might travel. That's a really good question, particularly because particularly in Lower Geyser Basin, we know that today there's not a lot of sagebrush that grows there, not a lot of artemisia, so that has to be coming from a long ways away. We don't have any other evidence of substantial changes like in synoptic climate patterns through this time, and the at least prevailing wisdom has been that throughout the Holocene and throughout really the post-glacial period, winter storm tracks coming up the Snake River Plain is like the prevailing, it has a lot to do with the prevailing wind. The interesting, I think we don't have a great proxy of paleo wind directions at these sites, but what I would suggest is maybe we could get around this a little bit by looking at nearby sites, which is sort of what we've done, looking at Cygnet Lake, Loon Lake, Yellowstone Lake, and those sites show a very different record than Goose Lake. And that's our biggest thing that suggests to us that the record we see at Goose Lake is a local change in vegetation rather than something that's happening on a regional scale. But yeah, this issue of distally transported pollen is a very challenging question. So you've got a question about, see on slide 37, I knew there was a reason I numbered my slides. Asking about this, this comes from Hurwitz et al. 2020. Let's see. Asking about where do the historical stream flow data come from? So these all come from, there's a couple levels of interpretation here, but I believe all of these data that Hurwitz et al. Are using here for the local scale are from dendro data. At the Corwin Springs, I believe it's tree rings in, I believe it's limber pine, and they also compare it with dendro records from Rocky Mountain juniper in Yellowstone. So I believe most of this comes from dendro data. I'd be happy to field any other questions or criticisms. And thanks everyone for the kind words otherwise here.
Hey Chris, this is Buzz. I got a question.
Lay it on me, Buzz.
Yeah, could you go back to your slide where you have you compare multiple AP NAP ratios from things like Signet, Yellowstone, and then you talk about your Goose record?
Right, this figure.
Yeah. So the fire activity record for the Yellowstone Plateau is Signet.
Mhm.
And your Signet arboreal to non-arboreal pollen record doesn't really look like it actually increases all that much through your middle Holocene to late Holocene period. So I was kind of curious as to like what other drivers do you think could be at Signet Lake for the increase in fire activity? Do you think, I mean, it's kind of about the same time that we'd expect to see more ENSO, so do you think that could be a factor?
Yeah, and it's a little tricky, and part of it, the difficulty might be in a poorly made plot. But I especially in the late Holocene, there is a little bit of an, I think there is an increase in arboreal pollen at Signet Lake. The possibly conflating factor is that Signet Lake itself is not densely surrounded by forest. It itself is situated in a little bit of a meadow. So there might be some site scale factors that could be at play there. But I strongly suspect that the increase in fire activity at Signet Lake is driven by biomass.
Cool. Okay.
Because climate's getting cooler and wetter, so it's not the climate driving it.
Sure.
Not directly.
Okay.
But I'd be happy to talk more about that offline, and Kathy can tell us why we're both wrong.
Are there other questions for Chris? Well, seeing none right now, Chris, let me thank you for a really excellent talk. Some beautiful slides, and we'll look forward to seeing our Rough Cut audience members in 2 weeks at our next Rough Cut talk. So thank you so much, Chris, and thank you all so much for coming.
Thank you all. It's an honor to give this talk. And thank you, Julia, for putting it together.
Okay, we'll see you all next time.